All right, thank you. Yeah, so I'm Keely Finkelstein. I'm a research astronomer at UT Austin in the Department of Astronomy and McDonald Observatory. And I'm here today to tell you about, I'm gonna actually pick this up so I can move around a little bit, about recently a trip I got to take observing at 40,000 feet aboard the SOFIA telescope. And so I'll walk you through what that was like. Here's the wrong one. There it goes. All right, and now I got it. All right, so what is SOFIA? SOFIA is a telescope aboard an airplane. It stands for the Stratospheric Observatory for Infrared Astronomy. And the telescope itself is just a little bit bigger than the Hubble Space Telescope. It's 2.5 meters in diameter. And it's a telescope strapped on the back of an airplane, actually a Boeing 747 SP, and the SP stands for Special Performance. It's basically a 747 that's a little bit shorter. They cut out some of the fuselage from a typical 747, so it makes it a little bit lighter weight. It can go faster and fly a little bit higher. SOFIA itself typically flies at about 40,000 feet. It can go even as high as about 45,000 feet. So at that altitude, you're above the terrestrial water vapor layer. You're actually in the stratosphere, hence its name, and you're higher than typical airplanes, which might fly at about 30,000 feet. SOFIA itself is a joint venture between the United States, NASA, and the German Space Agency. So we have a little bit of about 80%, Germany's in there for about 20%. And here's a little bit better picture here of SOFIA. You can see when you walk up to it, you climb up to it right from the tarmac. They wheel out the stairs. We have the nice little American and German flags on there showing that it is a joint venture itself. And what does it look like inside? It looks somewhat like a typical airplane. You'll see some other shots here in a minute, but the back half of the airplane is this big, huge bulkhead, and a lot of it is kind of open, and the telescope itself the mirror itself is right on the other side of this pressurized bulkhead. But the instruments, one of the instruments that we used, it's this instrument here I'll talk more about, it's on the inside of the bulkhead, and where we all sit is just down this way. We'll see in a little bit here. So the instruments are on this side. It's a big pressurized bulkhead, and the telescope, the mirror, is on the other side of the pressurized bulkhead, and it can open up once it's up at the right altitude. It opens up this door, and then the mirror's just out there, can stare at whatever it wants to. And so this instrument that you can kind of see here, again, it's maybe about the length, maybe about 4 or 5 feet this way in length, about the size of a little over 5 feet, typical length of a person, height of a person. And it's a big spectrograph, and the spectrograph itself is called XEs. And XEs stands for Echelon Cross Echelle Spectrograph. It's kind of a mouthful, but basically it's a spectrograph that operates at mid-infrared wavelengths. Steve was talking about, again, wavelengths that are redder than our eye can see. That's into the infrared. And this is kind of right in the typical kind of mid-range of light that's redder than what our eyes can see in the mid-infrared, which is, for this instrument, it operates at about a little over about 5 microns all the way out to about 28 microns. And this, again, is just for this instrument. There are other instruments on SOFIA that operate at different wavelengths, mostly designed for the infrared, but there are some that go down even into the optical and maybe a little bit beyond. The instrument, this XEs instrument, it was originally designed here at UT. We even built the prototype here in Texas. And the PI that's now actually led out of University of California in Davis, but a lot of the early work was done here at UT. And what all that kind of fancy stuff, all the echelon and the cross echelle, it's basically different types of gratings. It's an echelon grating, and then it's crossed with dispersed with another type of grating called an echelle grating. So the X comes from this cross dispersed part here. So here is a couple of us standing kind of in front of the instrument inside the aircraft itself. They don't let you get too close to the instrument. They kind of have this kind of warning part blocked off here. This is another astronomer. He's part of the instrument team, the XEs instrument team. He's actually an astronomer down in San Antonio at SWIRI. And the other 2 people that are here are 2 teachers that are teachers here actually in Austin, in Texas. And the reason why I was able to go with this group is that we have a group of teachers, of K-12 teachers, mostly actually secondary school teachers, all from Texas, that have been part of an ongoing program for about the real start of when SOFIA really started to get off the ground, which was in the late 1990s. So a group of teachers have been together from about 1998 all the way up until now, and we're still ongoing. And some of these teachers have been with us from the very start. A few are more recent, have only been with the group for maybe 5 years, or some have even been 10 years. But all these teachers, they meet on a regular basis. I lead the group now, and we meet kind of about 5 or 6 times a year. We talk about astronomy. They do astronomy. They take the astronomy they learn back into their classrooms. And they've learned all about infrared astronomy. They've learned all about SOFIA. And those that kind of signed up at the very beginning of this program, they really were kind of given this opportunity that maybe one day you might get to go and fly on SOFIA and do that. And so we had about 10 teachers that were able to fly finally this last spring in February and March. And 2 of them were on the flight that I was on. So it was a really cool experience, not just for me, but also for some local Texas teachers. All right, so besides just being awesome that there's a telescope strapped to the back of a 747, it's kind of like a typical observing run. You might go up to an observatory, you stay up late at night, you look at whatever you're going to observe, and it's kind of that same idea, but there's a little bit more to it. There's a little bit more planning, a very kind of a rigorous schedule the day of the event, the day of the flight. There's a welcome board safety card, just like you might see on a regular airplane flight, but again, it has a few more details, a few more safety instructions that aren't even typical for definitely aren't typical for a regular observing run at a ground-based telescope, and are a little bit different than you might see on your regular airplane. It might be a little bit hard to read, but this was kind of our schedule for the flight day. I didn't actually have to show up this early. I didn't have to show up at 7:30 in the morning, but we kind of had to show up starting around noon. We had to do an initial training, kind of a training session around 12:30 or 1. This is kind of the schedule for some of the other, the people on the ground that are helping keeping everything running. But then everybody kind of had to start to get together around 3 o'clock or so. They had a crew briefing, and they have an overall mission briefing, and so this includes the pilots, all of the support staff, the people that are going to be on the airplane, the instrument team, the telescope team, us as these guest observers. And then basically we had to start to get on the airplane by a little bit after 4 o'clock. Had to make sure we were on the airplane by 5 o'clock. The doors would close like kind of at that exact time, and we were taking off right at 5:15. So no delays here, no airport delays here. And again, you have this very rigorous schedule, and we all during this time in between is when we were actually observing, and then we landed right almost about 4 a.m. in the morning. So we were observing for about 10 hours. And the whole process was quite extensive. All right, so here's a little bit more of this kind of in-depth security or safety that you might have to go through if you ever get the chance to fly on an airplane that has a telescope on it. So a lot of the stuff, there's the typical things like, yes, there's a life vest somewhere behind your seat, but we also have this extra piece of equipment that we had to carry around with us sort of at all times, especially if we got out of our seat and left our seat. It was called the Emergency Passenger Oxygen Smoke Hood. And basically, again, if you left your seat, if you were going to be walking around the airplane, so you either go to the bathroom or maybe you got to talk to the telescope team, you just kind of had to sling this thing over your shoulder and carry it with you. And it's basically this smoke hood. But just in case, I guess if the airplane or the telescope or something catches fire and you're stuck at high altitude, you put this on, and it essentially gives you more time, more air to breathe. It's giving you a whole kind of extra coverage and stuff. So, I wasn't ever too worried about anything going wrong, but it was definitely interesting to have this and have to carry this around with us. All right. So again, here's another extra safety procedure we had to have. These are 2 other teachers that got to fly on a different flight, but they're kind of showing off. We had to wear these sort of reflector little vests or straps with us when we were getting on and off the plane. It wasn't so much an issue when we were first getting on because it was the middle of the afternoon, but when you're leaving the plane in the early morning because you're kind of walking on the middle of the tarmac, you had to have these extra little safety things on with you. So again, little extra safety precautions. And this is kind of a good shot to show you what really it looks like inside this aircraft. And this is an old, again, it's a 747, a Boeing 747. I think this was originally a Pan Am airplane that got sort of overhauled and NASA bought and made use to house the SOFIA telescope. So some of the stuff they took out and put in their own things. So there's like kind of like basically like what you would see like if you go to NASA and you're in their kind of missions director, missions headquarters. There's lots of stations with telescopes. Right here is actually where the mission director sits, and she's basically in charge of the whole show. She communicates with the pilots, she communicates with the telescope operators, the instrument science team, anybody else. And so she kind of has the lay of the land. Other science team members can sit here. The instrument science team sat up here, and the telescope operators sat here. And we're all facing towards the back of the plane, and the telescope and the instrument are all back here. It would get, I know it's kind of hard to tell, it would get actually pretty loud on there, and I'll kind of show you here in a second. I have, I think, a movie to play. It was loud inside there. It wasn't quite as nice as comfortable as a regular airplane, so we all had to wear sort of these headphones and everything to communicate with each other. It was also a little bit colder than a typical airplane flight, so everybody's kind of bundled up. Here's just to show you what our flight director. Again, her name is Nancy, and she was in charge of running the whole show. You can see her nice headset there. Here's kind of what her station looked like. So she would see our flight plan. She would see what the telescope was doing. She would see any other kind of things that she needed to know to operate. She would have there at her disposal. This guy here, his name is Dr. Matt Richter. He's the principal investigator of the XES instrument, and he actually started here at UT when XES was first being developed. He was a postdoc here at UT, and he's since is kind of running the show for XES, and he's now at UC Davis. So he's sort of the head honcho for this instrument, and that's him there, kind of looking a little bit happy because we're getting some data in here on the screen here. So he's checking out the data as it comes in. And this is what a typical flight plan might look like. This was our flight plan, the one that I was on, and it kind of looks a little bit crazy. We left here out of California, you can kind of see that, just outside of LA, out of Palmdale, California, and the black parts is sort of our takeoff or landing, but all of the blue parts are different things that we are pointing and staring at, the different targets, the different observations that we're making. You might even see some things that look kind of familiar. You may recognize any names there on the blue part of the tracks there. I heard Betelgeuse, Callisto. Yeah, so we're looking at actually some pretty cool, some nearby stuff. Again, taking spectroscopy of all these different objects. And so for a given kind of track, until you see the sort of the flight path change and where you kind of see one constant name, we have a kind of a constant heading. The telescope, the aircraft itself is flying in one heading, and the telescope stays fixed, pointing at whatever that object is for that amount of time. And you can kind of see the times. They might vary from an hour long or hour and a half. The typical time you might point at one object was right around an hour. And if it took you a little bit longer to get on to this target, if you didn't get on there right at whatever that time says there, and you don't get that whole time. So it might only have, you're supposed to be on that target for an hour and a half, but if you could only, get onto it for an hour, that's all you get, because basically the aircraft has to keep this heading. It has to kind of keep on these time things. And so once you get to this point, you basically have to stop and start and turn the aircraft and turn the telescope. So we went down pretty far south in our flight. We flew way out in the Pacific, kind of down past Mexico here, and then kind of made this big sort of came straight back up and over. And again, this whole total flight time was about 10 hours. One of the very cool aspects that was definitely kind of a once-in-a-lifetime opportunity was that for the ride back in for our landing, I got to ride in the cockpit in the jump seat and got to kind of sit back here right behind the two pilots that were flying the aircraft and listen in on what they were doing, what they were saying. So what I wanted to show you here is this is an actual movie of the telescope itself. And if you kind of look closely, kind of follow this instrument, maybe kind of look at it in relation to like this netting here, what do you see? What's happening to the telescope? What does it look like going on? Looks like it's moving, right? Looks like it's moving. So actually, this is us. This is the aircraft itself. We are the ones moving. The telescope itself stays completely fixed at whatever it's pointing at. It has gyroscopes. The telescope itself is not moving. It's us that's moving around with it. So it's kind of this little bit surreal effect when you're inside of it. and you realize, oh, it looks like the telescope is bouncing around, especially if you come across any kind of little bit of turbulence. But no, the telescope is actually staying perfectly still, perfectly fixed at whatever it's staring at, and the airplane itself would kind of move around. It would be the one jumping around, and the telescope wouldn't. But you can kind of tell how much we're moving just by staring at the telescope. All right, so just to show you kind of a few things of what we actually did observe on a couple of these observing runs. Some of these, again, are kind of well-known things, or at least well-known parts of the sky that you might know. We are observing a big, massive protostar, so a big star that's in the process of forming in the Orion Nebula, so towards the Orion constellation in the Orion star-forming nebula. Here's another object. Anybody have any guesses of what this might be? Just by looking, this is the guide camera. You can kind of see there, both on the left and the right. Oh, I heard it. Somebody's good. Jupiter. This is even a better kind of zoomed in view here. So yeah, we actually pointed at and stared at Jupiter for a little bit, and you can see some of its moons there, kind of really light. It's big and whopping bright, but we're looking at it in the infrared. And again, this is just the guide cam image, and we're taking a spectrum of it. Here's an image kind of just showing you what some of the data looks like. It's kind of hard to see because it's black and faint. But again, we're taking a big, huge, high-resolution spectrum of whatever objects we're staring at. And so all of this is basically spectrum kind of in a continuous wavelength band. And so these are just sort of strips that, and you can kind of see some of this is sort of basically like skylines or sort of noise lines, some of the brighter things. But some of the stuff that you see on there is actually emission coming from the object that we're looking at. And what else? So this kind of looks like this is sort of just a raw data frame. It doesn't look that exciting. But what else has SOFIA, and especially this instrument that I used and that we used as part of this program, what has it done? Has it had any cool results? Well, yeah, a couple of cool things that have come out just in the last year. XES itself actually only has been on the SOFIA telescope for a little over a year. Its first, what we call commissioning run, happened in the spring of 2014, and then it had a second commissioning run kind of late, like January through March of 2015. And so this is actually some observations it took of Jupiter, and you can kind of see it's actually all molecular hydrogen, but at different wavelengths, again, also in the infrared. But you can kind of see parts where it's really bright, kind of molecular hydrogen, sort of in we call limb brightening in the edges of the atmosphere here. Another cool result that they just kind of published recently from using this instrument, all of this stuff that you actually see here is actually water. These big, huge features here are actually water vapor absorption from Earth's atmosphere. But this little kind of small little dip here is actually detection from a protostar, from a really massive protostar that's showing that there's water vapor. So water in the disk, or maybe in the surrounding material, the molecular material around this newly forming protostar. So just kind of cool. Think about it. Some of those products that we know that are important for us here on Earth and life on Earth, maybe you're in the process that we can detect them and forming around this massive star that's in the process of forming. All right, one last slide, just kind of a fun sort of takeaway. The instrument itself, again, as I mentioned, it's called the XES instrument, and that stand again for that's its official sort of symbol and thing. But they have an unofficial mascot. So because it's XES, their unofficial mascot is the XMen. And so for each of the different kind of commissioning runs and observing runs that it's taken over the last 2 years or so, they've had a different XMen as their official or unofficial mascot. So for the flights that we were on, Wolverine was the unofficial XMen mascot for the XES instrument. So here they had this little guy actually on the plane with them, and this was at the end of the night of one of the flights. And these are two of the instrument leads, and they were dressed up wearing some of their XMen gear. So yeah, it was a great experience, and I was happy to share it with you. So that's it. If you have questions, happy to take them.
All right, thank you. We have time for some questions for our second Dr. Finkelstein of the night. Shout if I can't see you. In front, down here, yes.
Yeah, so I launched this telescope when you already have the Hubble.
So yeah, it is the same diameter, but they actually operate, for the most part, at very different wavelengths. Hubble only goes out to the near infrared, so maybe out to a few microns, and this can go out to, this instrument again kind of goes out to about 20, 30 microns, and some of them even go out to even longer wavelengths. And So yes, it can do even more than what Hubble can do. And the other good thing about it, or kind of cool thing about it, is that while Hubble is great and it's above the Earth's atmosphere and we can go and service it, we've set servicing missions to it, that costs a lot of money. I think it's about like $2 billion per servicing trip that we've had to spend each of the times we sent astronauts to service Hubble. And while this instrument, this telescope's not cheap, we can do all of the fixes, all of the work on it right on the ground. It does have some disadvantages. It's not, I mean, it's still not, you're not getting quite all the way above Earth's atmosphere, right? So you still have some, effects that basically why we can't observe very much from the ground in the infrared is because of all of our atmosphere and all of the water vapor in Earth's atmosphere basically absorbs all the incoming infrared light. So basically it's really hard to observe infrared light. And so we can we're compensating for that a decent amount by where SOFIA flies, but there's still some parts that's hard to do. I don't know the total cost per flight. I think the total overall cost of the aircraft was maybe a little over $300 million, and the telescope and everything. And I don't know what the annual budget for it is, but yeah, it flies usually, I would say, like 3 to 4 times a week when it's in operation. It's not every single day, but it's usually multiple days per week. And then so it was flying nonstop this last year from September of 2014 all the way through April of 2015. And actually right now they actually took it. It's actually down in New Zealand in the southern hemisphere, and it's doing some flights from the southern hemisphere from June through maybe even through the end of this month down there. And then it'll come back up here and probably start doing flights again sometime in September.
Okay, in the middle here.
So the view from the telescope isn't perturbed by the turbulence of slipstream?
Sorry, the view of the telescope itself? Yeah, it basically just kind of, you're seeing, so we don't actually see the mirror itself, right? That's behind this big pressurized bulkhead, but you can see the instrument. And so you can see it looks like the telescope is moving, but it's really not. And it's really just...
I'm saying 500 mile per hour wind blowing through an open window.
Yeah, if they have really big storms or something like that, or really high clouds, like some of the really high, whatever they're called, clouds that can go super high in the stratosphere, they'll try to keep a lookout for that, and they'll maybe avoid that area if they need to. They'll alter the flight plan. I didn't have experienced any really bad turbulence when I was on the flight, so it was never too bad of a problem.
There's another one in the middle here.
Was the American flag backwards?
Was it? It could have just been, I don't know. I'll check. I didn't actually catch that. Good catch. I'm not sure in the answer to that question. The question was, why was the American flag backwards? Somebody noted apparently the American flag on the side of the aircraft was backwards. Oh.
It's flying in the direction that the aircraft is moving, and so it's being pushed back, so the stars are on the aircraft being pushed back towards the back.
All right, thanks. See, I even learned something. Thanks, Brian.
Okay, we've got time for one more question. Anyone want to jump in with another question? Yes, at the back.
Well, I don't know the whole historical reason for why that. I think a smaller plane would have been cheaper, but you definitely want something with enough structural support. You're still going to have a really heavy instrument. Like the telescope itself is, I can't remember the exact weight, but it's a number of tons. And so you have all of this equipment, and the telescope itself is really heavy. So you do want something big enough to support that, but still, so I think that's why they chose the 747 SP, that model, which is a little bit more compact, but still is a big, solid aircraft.
All right, thank you very much, Silver SFR.